So let's look at the temperature graph, and that's what's on your next page. So here's where you can take your notes, but I'm going to look at the bigger graph on the PowerPoint. What our goal is here is to sketch the derivative of the temperature graph. So here's what we're looking at. What's happening here is that the temperature in degrees Celsius is dependent upon how high you are, on what the altitude is in feet. Okay? So when you're at 0 feet, basically on the ground, then it looks like the temperature is about 18 degrees Celsius, wherever that is. That's about right here. And then as your altitude increases, your temperature actually decreases until you get to 1,000 feet. And then at 1,000 feet, the temperature starts to increase again. And it continues to increase very, very fast, a very steady, sharp increase at first, but then at some point it kind of seems to start leveling out and becomes almost, but not quite constant, from 3,000 feet to 5,000 feet. And then it starts to decrease, so it's getting colder until you get to 7,000 feet. And then there's a little sharper decrease, a little greater steepness of the decrease until you get to 9,000 feet. And then from 9,000 feet on, it seems like the temperature is just plunging. So what's happening as you get higher and higher and higher is it's getting colder and colder and colder. Okay? So we want to do a slope graph of that. So here's how we're going to think about this. And we're going to do it right on this same graph. Notice that when the slopes of the tangent lines to the graph are 0, positive, and negative, okay? We don't ever actually have a 0 tangent except right here. So at that point, our derivative graph is going to be at 0. Now, when are the slopes positive? Well, the slope is positive from this point on until we get here and here. Somewhere in here, it kind of becomes 0 again. I would say right about there. It's close to 0. So that's at about probably 4,000 feet, close enough. So it's at 0 at that point. But from here until here, it is always positive. Before we hit this point, we see here that it was always negative. And then after we hit this 0 point, it starts going down again, so it becomes more and more and more and more negative. So let's see if we can use that information to sketch some idea of what this thing looks like. Starting out, the slope graph is negative. And it looks like it's increasingly negative. So it's going to come from down here, and at this point it hits 0. Then it becomes positive until it gets here. And we have to look at it and say, okay, it's kind of a sharp increase and then a slow increase. So it's kind of going up and slowing down. And at this point, it drops back down to 0. So I probably could have shaped that a little bit better. And then after that, it becomes negative, and it becomes This is slower, 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 faster, 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 so it becomes more and more and more negative. So the slope graph would look more like the red curve that I drew. You agree? Remember, this is the slope, what's going on with the slope based on what's happening with t of h. So this graph is actually the graph of the derivative of t of h, t prime of h. And the thing to take away from this is when h is equal to what number and what number, the slope of the graph is equal to 0. Well, that happened at 1,000 and 4,000. So therefore, t prime of 1,000 is equal to 0, and t prime of 4,000 was equal to 0. And then looking at this, when h was 500, which is probably right about here, the slope appears to be it's like a drop of about 5 over 1,000, so the slope appears to be 5 over 1,000, or 0.005. And then when it's at 1,000, it's 0. When it's at 1,500, which would be right about here, then it looks like the slope is, I'm just trying to guess from points, it's like over that 500 period it has gone from (13) to 16, so that's 3 over 500. Which is a decimal would be about 0.006. And then at 5,000, which is right here, looks like the slope might be, let's see if I can connect up these two. This is the 0.3000, and it looks like 25 degrees. And this looks like the 0.7000 and 20 degrees. So that's a change of 4,000 on the numerator over in the denominator, over a change in degrees of 5. So let's change that to a decimal. Yes?
Why are the slopes all positive?
They're not. I need to go back and actually adjust that. Thank you for bringing that up. Okay, so coming back here, t prime at 5,000 is going to be negative. And t prime at 3,500, which is about here, it's going to be positive. I think I missed that one. I'll come back and get that one. And at 1,500, it was positive. This was 0. And at 500, it was negative. So those were negative. Now let's see if we can figure out what it is at 3,500. 3,500 is probably right about there. looks like that might be 3 degrees change over 2,000. Or about 0.0015. Now, take into account, this is not precise. This is not a precise science, okay? Because you can tell that it's really hard to determine what slopes are by trying to guess what points are on the graph. Because it all depends on how accurate the graph is, how big the graph is, what the increments are as to what you can tell. So I don't want you to feel like you're having to be very precise. You're not. And if you look at this table, it's not really particularly close to mine, and yet it's similar. Okay, the first one matches, the second one matches. Here, my guess was 3/500, and they say that it was 0.008 because they had a better interpretation of the graph. It says at 3,500 it was 0. Well, okay, it might have been close. I couldn't tell by looking at the graph. This is a fairly close to 0 slope. And then at 5,000 it was negative, and they got the same values that I did. But there again, remember, I'm guessing. I'm trying to guess 2 points on that tangent line. So using the information that they have, they say that these are the actual points, and they say that the slope graph looks like this. Now I'm going to put a side by side with what I sketched, and believe me, mine was a sketch. So my sketch was kind of lopsided here. That should have been actually more like this, but you got the same general idea. So, you know, I'm not expecting you to be perfect at this. If I'm not perfect, you're not going to be either, okay? This is much more about the idea of what's happening with these than it is about being perfect. So, okay, we're going to try one. And you actually do have the points to actually connect on the next page, but the you try this one is on the next page. So let's see what we can do with this. So help me out here. Fortunately, we don't have too much of a curve here. Most of this is straight lines. So tell me, what's happening to the slope of this line? It's steadily increasing. In fact, this is a linear part of the function. Can you find an exact slope just looking at the graph? I'd say it was 1 because here is the point 0.03 and this is the point 2.1, so I'd say the slope is 1, okay? So looking at just this part of the graph, the slope is constant and it's positive because that part of the graph is linear. So we can actually tell what it is. So from back here behind -6 until we get to 2, that graph's slope is 1. You in agreement? Okay, the next chunk we want to look at is when it goes from -2 to 0. What's going on now? What's the slope now? It looks like it's -1 because again, it's linear. what was the value of the slope right here?
Sure.
You sure? At that point, at -2. Can we talk about what the slope is at -2 on those two joining together linear functions? Think about limits. Limit coming from the left, limit coming from the right. The limits do equal the value of the function, but can I draw a unique tangent line at that point? Can I draw a single unique tangent line of the graph at the point -2, 1? There's the tangent line. There's another tangent line. There's another just barely tangent line. Do they all have the same slope? Is it all the same tangent line? No. So what can I say about the slope where two linear functions join together and make a corner? Is there a slope? At that one point, is there a slope? Not this time. Not this time. Yes, it's going from positive to negative, but the slope at 2, because it's not curved, remember it has to go gradually from positive to negative. It's not curved. We can't draw a unique tangent line. So in actual point of fact, my derivative graph does not exist. So both of those are open circles. It might not look very open because my marker's kind of old. But there is no derivative. F prime is not defined at -2, okay? So, now we're at 0 and we're moving onward. Now obviously the slope is different this direction than it was up to that direction. It's changing. Where do you think it actually starts to make its transition? What's your best guess as to what x value it starts to transition from going up really, really fast to starting to level off? What do you think? I think at 1. Does everybody else agree? Looks like at 1, up to that point, it's going up pretty fast. Then after that, it starts to level off. But is it still positive? Yeah. So let's say up until 1, the slope looks to be more like +1, but then from 1 to 2, it looks more like maybe a half. And then from 2 onward, it gets flatter and flatter and flatter. But it's all still positive until, I think it looks like by the time you get to about 6, it looks like the slope's practically 0. So I'm going to say that at 1, the slope is probably +1 again. But between 1 and 2, it's decreasing. And from 2 to 4, it's decreasing a whole bunch. Still positive. And from 4 to 6, it's decreasing even more. So it's getting closer and closer to 0. So here's what I think it looks like after that. And it's approaching 0. So there's F prime. What do you think? Does that seem reasonable? Now I know for a lot of people this is the most challenging part of the first chapter in calculus. And then for other people that are more visually and abstractly attuned, it's not as hard maybe as what some of the stuff in the middle was. Whether or not something's hard in chapter 11 depends on the way that you think. Depends on what kind of thinker you are. Do you need to see pictures? Can you think in abstract terms? Do you need to actually see it spelled out numerically? Which way works for you? So all of chapter 11 has been about rates of change of slopes, but it's been presented to you in a lot of different ways. This one is probably, I'm not going to say it's the hardest one, but for people that aren't visual learners, it might be the most challenging to figure out. So this is the picture that we're looked at for when x is less than 0. And then this is for when x is greater than 0. And I sort of left out the point from here to here, but it would be if you look back, since it was sharply increasing up to that point, then it would have been more and more positive. And that is in fact what the derivative graph shows. Now, if you could do one that's about this level of difficulty, then you're in good shape. I wouldn't expect to throw you in to that graph and you'd be able to do it just, in 2 minutes. That wouldn't be fair.
So sketching a graph like this is going to be something we'll see on the test?
Probably not sketching the graph as much as talking about what happens at various places. It'll be very similar, and I think if you look, there's the exercises in 11.5 are closer to what I would ask you. Now, one thing I wanted to point out to you here. Graphing calculators will draw slope graphs for you. So as long as you know the function, the best way to get the graph of the slope, or the rate of change graph, which is what we're going to call it, and a lot of times it is better to have a graph of the rate of change than a formula for rate of change, we're going to be able to do it this way. So I'm going to bring up the calculator and walk you through. Let's see, I think I'm going to need to do a little sizing here, so bear with me. So for the one that we're going to do, we're going to find the derivative of the graph of x to the third power. And I don't know if you knew it or not, but there's actually a third power key on your calculator on math. Or you can use the caret and the 3. So having put that in there, I'm going to go down to Y2. And we're going to press math, and we're going to go down to nderiv, which is number 8 on math, and we're going to do the derivative of the function that's in y1. Now, since the function in y1 is relatively short, you might opt to go ahead and just say it's x cubed. Or if you have a big, long, ugly function that has lots of terms, then it might be easier to hit your bars key and go over to y-vars and choose function, and then enter again to choose y1. But again, you can just type in the formula for the function. And then you have to type in x, because that's and for those of you that have 84s, you're going to have to put the x in first, because yours brings up kind of like a little plug-in menu. So on the 84, you're going to put in the x first, then the function, and then x again. So on the 84, this is gonna look like, on the screen before that, it's gonna say D over D box. That's gonna be X. And then there's gonna be a parentheses, and you're gonna wanna put the function in there. And then down here is going to be another little box, and you're going to put an X in that box too. So there's your TI-84, more like what it looks like. And then at this point, we're going to graph it, and I know y equals x cubed shows up just fine on a -10 to 10 window, so we're going to just hit zoom and choose standard. So there's our function. And there's the derivative. So if you need to figure out which is which, you just hit trace. And at first you're tracing on the function, so you can see the function is the cubic looking function. You probably know what that looks like anyway. But if I jump down to the derivative and trace, notice that the derivative is a quadratic function. And one good thing we can do with this is we can also go and look at the table. And right now I've got this one set to auto. So notice that when x is -3, the slope is pretty steep. So if you look at this graph over here, when x is -3, which is right about there, look what your slope is. It's pretty steep. But when x is -2, it's still pretty steep, but it's not as steep. It's leveled off quite a bit. It's more like that. And then when x is -1, it's still positive, it's still increasing, but it's only 3. So it's not nearly as steep as it was before. And then when x is equal to 0, the value of the function is 0, but that doesn't really matter to me because what's happened here is that the derivative is also equal to 0. And it's giving it to you in scientific notation because it's trying to do a numerical process. It's not actually doing an algebraic process, but that's 0. So when you get to x equals 0, you actually do have a slope that is 0. And the value of your derivative graph at that point is going to be 0. Okay? And then when it gets to 1, notice over here, it's still positive, but it's not very steep. At 2, the slope is much more positive, much larger, so it's much steeper. And 3, it's very, very steep. So the same thing that's happening on this side is being reflected on this side. Now talk to me. Tell me, why is it the slope would go to 0 and yet it's positive on both sides? Normally, when you have a 0, don't things change signs? But it didn't this time. That function didn't reach a maximum or a minimum at 0. What's going on with the value of x cubed at 0? It did increase and increase and increase, but it went through 0. And then it increased and increased and increased some more. Does anybody know what the name of that kind of point is? That's called an inflection point. Cubic graphs, fifth power graphs, they have inflection points where things stop being as steep for just an instant and then start going back up again. So they're positive, they flatten out a little bit, and then they shoot back up again. That's called an inflection point. It's when things change concavity is the math term for that. So at this point, we are finished with 11.5. There are 3 problems in the textbook that are worth looking at. I don't know if that's the right page number, but 3, 5, 7, and 17 in exercises 11.5 would be good ones for you to look at and practice. And what I'm showing you here is if you have